So Venus is the second planet from the Sun. Its year is 225 Earth days and its day is 243 Earth days. And that's right, you did hear it, the day is actually longer than the year. And it's very interesting, it's not, just doesn't stop there. It's not like all the other planets, it rotates backwards. It's also considered our morning or evening star. So it rises very early in the morning. If you ever get up at 4 a.m. and you see a bright object in the sky, it's probably Venus. It's one of the brightest objects in the sky after the moon and the sun. And when astronomers were looking through their telescopes very early on, they saw these thick clouds and they just could not see through these clouds. Nowhere would the cloud break for us to be able to determine what the surface looks like. So we had one option, and that was to go there. So Mariner 2 in 1962 went to Venus and it detected that the surface was very hot. Now there was a Mariner 1, but someone left off a minus sign off an equation and it crashed into Earth's ocean. No matter, $6.6 million later, they all fixed it by Mariner 2, so it was fine. The Russians went in 1967 with Venera 4, and the Americans also thought, well, we better go too. So they sent Mariner 5, and this detected a little bit more about the atmosphere, so density, pressure. Most interesting, Venera 10 in 1975 sent back the first surface images. Pioneer from NASA spent a decade mapping the surface with radar. We can't see, so we have to use radar to detect the surface through those very thick clouds. So the Russians thought, no, we better send our Venera landers, our Venera probes as well. So in 1983, they also mapped the surface. NASA thought we'll do it a little bit better. We'll image the surface with high resolution. So they sent Magellan in 1989. This was very effective. It actually mapped 98% of the surface. So we got very good data back from this mission. Then European Space Agency felt a little bit left out, so they sent Venus Express in 2005 to tell us a little bit more about the atmosphere this time. So we consider Venus to actually be Earth's twin. And why we do that is because it actually shares a similar size, shares a similar mass, a similar density and volume. So on home, on our planet Earth, we have nice temperatures, well, what we think is nice. So around an average of 14 degrees Celsius. That varies. It's cooler at the poles, warmer at the equator. The pressure is also quite hospitable as well for us. We love it. Our pressure's at 1 bar on the surface. We have surface water, like what Craig was actually saying, very important for us. And plate tectonics, same thing as what Craig was saying. Crust is being created and being destroyed. Now looking to Venus, its average surface temperature is 462 degrees Celsius. So lead melts at 328 degrees Celsius. So it's actually easy for lead to melt on the surface. The pressure is 93 bars. So that's the same as us all travelling 1 kilometre below the Earth's oceans. So it's very, very dense. We have no water on Venus. And one of these reasons may be from what Craig was mentioning was a runaway greenhouse effect. So in the very early history of Venus, there may have been a global ocean. And at that time, the sun was brighter, which meant that the surface temperatures were high. So when you're getting warm temperatures, you're getting greater evaporation, which means you're putting a lot of vapour into the atmosphere. Now, water vapour is very efficient at keeping heat locked in. It doesn't allow it to get back into space. So what happens is your temperatures increase. It means you evaporate more water vapour in the atmosphere. And this keeps going and going and going until you evaporate the ocean. It's also considered to be a one-plate planet. So we don't see any evidence for crustal destruction on Venus. So maybe, instead of calling it Earth's twin, we might be able to refer to Venus as Earth's evil twin. So we're not considering all these surface conditions, the differences between Earth and Venus, we're not 100% sure of the tectonic and volcanic processes that sculpt the surface. And before we do that, we need to understand the thermal structure of the lithosphere. And this is what my PhD has been trying to do. So before we go into too much depth, I'll first define what the lithosphere actually is. It's the rigid outer shell of a planet. It consists of the crust and the upper mantle. So one of the regions that I've been looking at is called Atla Regio. And Regio just means rise. So we could technically call it Atla Rise, but it doesn't sound as nice as Atla Regio. So I'll refer to it as Atla Regio from now on. And it's actually a 2,000 kilometre rise on Venus located along the equator. So it consists of 3 large volcanoes or mons. We have Saphus Mons, Oza Mons and Mat Mons. And Mat Mons is about the same elevation as Everest on the Earth, so very large. It also has 3 large chasma or rifts, Parga, which trends easterly, Dalai that trends southwesterly, and Ganus that trends north to northwesterly. So we think that 3 main processes actually produce the topography at Atla Regio. And the first is the lithospheric thickness, dynamic uplift, and flexure. And these are what we'll be looking at in turn today. So let's first look at the lithospheric thickness. So elevation relies on the lithospheric thickness as well as the thermal distribution. So if we change the lithospheric thickness, we change the temperature distribution. So if we thin the lithosphere, we're making everything hotter. It's more buoyant, we're getting higher elevations. And it's a little bit similar to if we would have a cork sitting in some water. So cork is not very dense, it's very buoyant. So you can see that most of the cork sits above the surface. So this compares if we would thicken the lithosphere, we're cooling it, we're making it denser, we get lower elevations. Same as an iceberg. So it's very dense. What happens is most of the iceberg sits below the water and we see very little on the top of the surface. So here is one of my models from my PhD that I've been working on. And the lithosphere is everything that's blue to yellow. So this is our boundary here. And you can see where we have the large volcanoes, we've thinned the lithosphere, which means it's quite hot here. It's more buoyant. We're getting those great elevations that we've seen before. This compares to areas away from the volcanoes. The lithosphere is much thicker, it's cooler, it's denser. We're not seeing those high elevations. Same thing at the rifts. The rift, compared to other areas, is actually quite elevated. We're getting thin thermal lithosphere, it's hot. Compared to areas away from the rift where the lithosphere is thicker, it's cooler, it's denser, we see those lower elevations. So we think that most of Atla Regio's topography is supported by just changing the lithospheric thickness. So we think we could also be getting some dynamic uplift as well. So we'll have a look at that now. So what is dynamic uplift? Well, if a hot material rises from Venus's deep interior towards the surface, it can actually create uplifted topography. And this is similar to a hot air balloon rising through the atmosphere. So inside the balloon, the air is more buoyant, it's warmer. Compared to outside the balloon, it's cooler, denser air. So this contrast actually causes the balloon to uplift, much like we would with our plumes. So we think at Atla Regio, those 3 large volcanoes that we were looking at needs about 1.5 to 3 kilometres of dynamic uplift. So let's have a look at flexure now. You might be wondering, what is flexure? Well, flexure is if we load the lithosphere with, say, a volcano in this instance, the lithosphere will be depressed below the volcano, and the surrounding area will bulge upwards. Same if you will get a ruler and you place a load by pushing down on either end of the ruler. So here's your load. You will see this, the area next to the load bulges upwards. And it's the same if you get a kitten on a trampoline. So if you place your kitten on the trampoline, the trampoline will be depressed below the kitten and all the area around will bulge slightly upwards. Same thing as Flexure. Plus it's a really cute kitten. How could I not put him in? So cute. So we think that we might be getting 500 to 1.5 kilometres of flexure below the volcanoes, particularly below that really large Everest-sized volcano. All right, so we think that we're seeing three main processes producing this topography in Atla Regio. Lithospheric thickness, followed by some dynamic uplift and some flexure. And that's it.